Hey guys, this is section 10.2 where we talk about thermodynamics of ion formation and solvation. So back in the last section where we talked about enthalpies, Gibbs energies, and entropies of aqueous ions, they were based on the standard of hydrogen having a value of 0 for its Gibbs energy of formation, which gave us delta H of solvation of hydrogen is 0, and same thing for the entropy. We call those conventional values because they're based on the convention of hydrogen ion being 0. Now, with calorimetry, what we can remember, the thing we can do is we can measure these values, delta G, delta H, delta S, for formula units, entire formula units. Sodium chloride, silver bromide, what have you, but not for individual ions because you can't buy a bottle of chloride ions because you need the counter ion in there. Otherwise it's unstable. So what we're going to do in this section is see how we can actually calculate the absolute or thermodynamic values for the individual ions. And to do that, we're going to take advantage of the beautiful, beautiful property of state functions. Gibbs energy is a state function, so that means it doesn't matter what path we take, the change should be the same as long as we start and end up at the same places. So experimentally, what we can do is what's up here in the green. We can do the experiment, get the ions, and measure values which allow us to get the delta G of reaction, which is negative 131.2 kilojoules per mole. Now, our theoretical path, would be to take the separate molecules, hydrogen and chlorine, dissociate them into gaseous atoms. This energy we call the bond enthalpy for the enthalpy, bond energy. Then take these gaseous gaseous neutral atoms and make them into ions by adding an electron to chlorine to make chloride, gaseous state still. Removing an electron from the hydrogen atom to form the hydrogen ion in gaseous state still. And then solvating these, taking the chloride ion in the gaseous state and dissolving it in water. Same thing for the hydrogen ion. So it ends up we know all these values. We know the bond enthalpy and the delta G for the bond of hydrogen, chlorine. We know this would be the ionization energy. This would be the electron affinity. So the only thing we don't know here in this, guys, in this circle are the delta G of solvations. Delta G's of solvation. So it ends up that if you add up this number, this number, this number, and this number, you get 1,272 kilojoules per mole. So we know delta G of reaction is equal to those numbers, which is 1,272 kilojoules per mole, plus delta G of solvation of the hydrogen ion and delta G of solvation of the chloride ion. But we know that what it is, the delta G of reaction is negative 131.2 kilojoules per mole. What that means is that the sum of the two delta G of solvations is equal to negative 1,403 kilojoules per mole. Definitely significant, definitely important. What we're going to do here is use something called the Bohr Model to calculate the Gibbs energy of solvation for the ions. And once we know the Gibbs energy, we can get the delta H and the entropies. What the Bohr Model is, guys, it's a simplification. And what the simplification is this: it treats the solvent as a uniform liquid. It's the same throughout, and it has some one dielectric constant. Dielectric constant is basically a measure of how easily it can break apart an ionic compound into its separate components, or how easily it can solvate charges. And the ion in the Bohr model is treated as a charged sphere. So the idea is we know that at constant temperature and pressure, the reversible non-expansion or non-PV work is equal to the delta G. And because this is solvation, it's equal to the reversible non-expansion work for this process is equal to delta G of solvation. And what that will be the work, we can think about it. Here's how we think about it in the Bohr model, guys, is we think about it as the work of taking a neutral gaseous atom, like a hydrogen atom, not a molecule, or a chlorine atom, and making it into the solvated ion. Q here stands for the charge, so +1 for hydrogen, -1 for chlorine, or whatever. and this is aqueous and it's in the solvent, minus the amount of work that it takes to basically remove that electron from that atom in the gaseous state. So the idea here is that, we have to remove the atom and then we solvate it. Here, remove the electron or add the electrons, and then solvate it. And here it's just how much work to either remove or add the electrons. So the difference between the two is the work done on or by the system by solvating that ion, which is what we're looking for. That's the idea. So it ends up from electrostatics. We know that the work, we can calculate it with this integral from 0 to the charge dq over 4 pi. Epsilon naught's a constant. It's the permittivity of free space. R is the radius of the charged sphere. And so you do this integral, we just get q squared over 8 pi epsilon naught r. The work going from, the gaseous ion to the solvated ion is the same thing. Only it ends up being that the difference is that we're integrating over 4 pi epsilon naught, still the permittivity of free space, times epsilon r, which is the dielectric constant of that solvent. And r is still the radius of the charged sphere. And so we get q squared over 8 pi epsilon naught epsilon r times r. That's the difference right there. But it's significant. So that means that the delta G of solvation is just the difference between these two terms, which we can write this way. This is Bohr's model right here, guys. Bohr's model. Where what we've done is the q squared. Q is, we're going to write it as the number of protons times the charge on a proton or an electron. So Z is the number of protons. E is the fundamental charge on an electron, same as a proton. 1.60 12 times 10 to the minus 19th joules. Na that's Avogadro's number, and we've defined everything else in here. So what we see, the form of this equation, guys, is that all this stuff out front for a given species is constant. Well, R isn't. Z and R are different depending upon what species we have, right? And so is this. But the important thing about this, one of the important things, is that the dielectric constants are always greater than 1. If you go look at table 10.2 in the appendix, they list some and they're all bigger than 1, which means 1 over the dielectric constant is a number less than 1. And so when we do the subtraction, we get a negative number, which means that delta G of solvation is negative, which means it's always spontaneous. Solvation of an ion happens spontaneously. So now let's look at how good, we need to see how good this model is. To do this, okay, we have to, we need to know the experimental values for delta G of solvation for some ions. What we have, whenever you look them up in any table, this is always the conventional values. That is based on the value of the hydrogen ion being 0. It ends up, these can be calculated. It's not simple. It's beyond the scope of this class, but the results here are given in your text. And that is that the delta G of solvation of the hydrogen ion, absolute value, thermodynamic value, not actually 0. It's negative 1,090 kilojoules per mole. Heat of solvation of hydrogen ion is negative 1,050 kilojoules per mole, and change in entropy is negative 130 joules per Kelvin mole. So if we use these, we can, knowing these, we can find the absolute values for the, the thermodynamic values for delta G, delta H, and delta S of solvation for other ions, just like we did, for sodium in sodium chloride in the previous section. Now here's how we test it, guys. We know from the form of the equation from the Bohr model is that this is basically the equation of a straight line, y equals mx plus b, where this stuff in the parentheses would be, 1 over epsilon r would be the x. This would be the slope, and this times negative 1 would be b. The idea being, though, we should get a straight line if we plot delta G of solvation versus z squared over r. E squared, Na, 8 pi epsilon naught, those are all constants, and for a given solvent, water, for us, the epsilon r is going to be constant. So here are the results. Okay, this is that graph, delta G versus z squared over r, and it has qualitative agreements. It looks like this is more or less linear. These are all singly charged ions. Like lithium, sodium, potassium, like that. These are all doubly charged: magnesium, barium, calcium, what have you. And then these guys are out here. So this is more or less a straight line, but it's definitely not quantitatively agreeing, because this red dashed red line, that's what Bohr's model gives. And in this model over here, this graph, guys, the R that we use is the ionic radius that we get from the crystal structure, the X-ray crystallography, the radius of the ion. Over here, what's been done is they've included they use what they call the effective radius rather than than the radius of the ion. What the effective radius is, it's the radius of the ion plus the radius of the solvation shell. So so they include those molecules of water that are clustered around the ion, and they, to the center of those molecules, and it ends up it's different for an anion than a cation and so on. But by doing that, here's the important thing: much better quantitative agreement here. Now here's the thing, guys. Okay, so we can do this, but the values, the uncertainty in the delta G and the delta H that we get this way, that comes from basically the uncertainty in the crystal radius and the solvation radius, is plus or minus 50 kilojoules per mole. For delta S is plus or minus 10 joules per Kelvin mole. It ends up the uncertainty using the conventional values is much smaller. So that's what we typically use, are the conventional values. That is based on the hydrogen ion being 0.